Today, we'll be discussing the Dijkstra's algorithm in detail. If you do not have an idea about the working of the algorithm, please refer to part 1 where I have explained step by step with the help of an example. However, here is a short recap. The Dijkstra's algorithm finds the shortest distance from a source vertex to all the other vertices. In this example, S is the source vertex. So you can see the value 0 written within the vertex S. It indicates the distance from the source to the source is 0 and all the other vertices are initialized with the value infinity. The values written within the vertices indicate the shortest distance of the vertex from the source. In figure B, we identify the vertices which can be directly reached from S and hence the values of t and y are updated as 10 and 5. Next, we identify the vertex which has the shortest distance, which is y in this case. Now find out the distance from S to all the other vertices through y and update the distance of the vertices if the newly found value is less than the already estimated distance. The value of vertex y is made permanent. Now estimate the next vertex with the shortest distance, which is Z as shown in figure D, and identify the distance of all the other vertices through Z and repeat this procedure until all the vertices have permanent values. Now let's move on to the algorithm. First, let's discuss a few functions which are used in the algorithm. First, we have a function named initialize single source with arguments G and S, where G is the graph and S is the source vertex. All this function does is the initialization procedure. There are two values corresponding to each vertex which need to be initialized. One is D. D represents the shortest distance of the vertex from the source. And another parameter is pi, which represents the parent or the predecessor of the vertex. This parameter is used so that we can traverse from the vertex to the source through the shortest path. Now in this function, the for loop examines each of the vertices and the value of d for each of the vertex is set to infinity as shown in line 2 and the value of pi is set to nil as shown in line 3. Line 4 sets the distance of the source from the source as 0. Another important function that's used in the Dijkstra's algorithm is the relax function. Now before going into the details of the function, let's try to understand the relax procedure used in the algorithm with the help of an example. Let's consider the figure A. Here we have a vertex u and a vertex v and there is an edge between vertex u and v, and the shortest distance estimated from u to the source vertex is 5 and the shortest distance estimated from v to the source vertex is 9. And there is an edge from u to v which has a weight 2. The relax function checks whether the shortest path to v that is already estimated can be improved by going through u. And if it can be improved, the shortest distance of v is updated. Here we can see that the shortest distance to v which is already estimated is 9. Now let's see what's the shortest distance to v through u. It's already estimated that the shortest distance of u from the source is 5 and there is an edge from u to v which has a weight 2. Therefore, the shortest distance to v through u will be 5 plus 2 that is equal to 7. Now 7 is less than 9 and hence the value of v is updated as 7. Now let's consider another similar example as shown in B, where the shortest path that is already estimated from v is 6 and the edge from u to v is 2. In this case, again, the shortest distance of v through u is 5 plus 2 that is equal to 7. But please note that the already estimated shortest distance of v is 6, which is smaller than 7, and hence the value of v is not updated. Now let's come to the function. The relax function has three arguments u, v and w. Here u is the vertex whose shortest distance we make permanent and v is the vertex whose shortest distance we are trying to improve, and w contains the weights of the various edges. Now in line 1, v dot d is the already estimated shortest distance of the vertex v and u plus d plus w of uv is the shortest distance to V through U. Here W is a function which returns the weight of the edge UV. In this line, it is checked whether the distance through U is less than the already estimated distance. And if it is less, the value of D and pi of the vertex V needs to be updated, which is shown in lines 2 and 3. The shortest distance of V is set to the distance through U, and the parent of vertex V is set to U because now in the shortest path to V, the predecessor of V will be U, as shown in line 3. Finally, let's come to the Dijkstra's algorithm. The algorithm takes the graph G, the weights of the edges W and the source S as the input. Line 1 calls the function initialize single source, which was already discussed, to perform the initialization operations. Line 2 and 3 initialize two data structures S and Q to phi, and these data structures need some explanation. As we know, in Dijkstra's algorithm, in each step we find out the vertex with the shortest estimated distance and make the distance of this vertex permanent. Here, S is a set which contains the list of all vertices whose distances are made permanent. And Q is a Q data structure which contains all the remaining vertices, that is, the vertices whose distances are not yet made permanent. Initially, none of the vertices have permanent distant values, and hence all the vertices are inserted into the Q. This is shown in line number 4 and 5. In line number 6, we have a while loop which runs as long as the Q is not empty. That is, this while loop runs until all the vertices have permanent values. In line number 7, the vertex which has the shortest distance is removed from the Q using the extract min function, and it is stored into the variable U. Now in line number 8, the vertex U is added to the set S because we are making the distance of U permanent. Now the for loop in line number 9 examines all the vertices which are adjacent to vertex U. In other words, each vertex V is examined if there is an edge from U to V. And finally, by calling the relax function in line number 10, it is checked whether the shortest distance to V can be improved by passing through U. This is done by the relax procedure, which is already explained. I hope now you have a clear understanding of the algorithm. And this algorithm was taken from the textbook Introduction to Algorithms by Corman. We will be discussing the time complexity of the algorithm in the next video. Thank you.